now. Okay, so today's theme is one that is very exciting to me personally, which is domain adaptation, deep domain adaptation, and deep domain generalization. The reason why these themes are really exciting is that I find them to be extremely useful in almost every single application domain. They will be they are dealing with some problems that are really ubiquitous to nearly every single application. So what does these domain adaptation and domain generalization do? These has to do with learning from multi-source data. So what is multi-source data? So multi-source means that the data source where the data is generated can come from different places. For example, take some of my personal experience on previous projects. In medicine, a cardiologist might want to diagnose whether a person has, let's say, arrhythmia by looking into their ECG signals. And these signals can come from different patients. And so each patient is a different data source. Also, in manufacturing, we have these rotating machines like bearings or turbofan engines, and they have their vibration signals that indicates when they're working properly. And for different engine or different bearing, the different machines, their vibration signal can differ from source to source, that is from machine to machine. Also, let's say in geoscience, we have remote sensing data. Now we may have a lot of different planets such as Earth, Mars, etc. And these remote sensing data from different planets can also differ a lot. And also in astroparticle physics, you may want to use a telescope to detect whether there is an oncoming neutrino from the atmosphere. And in this case, you may have a lot of simulations done. So you have these simulated events. But in the meantime, the telescope is actually recording the real events that is happening in the atmosphere. So the simulated events and the real events are from different data sources. So for the rest of this presentation, we will call each data source a domain. And what we are dealing with, is the discrepancy of distributions across multiple domains. So for example, let's take the ECG signal as a special case. So you may want to classify each ECG heartbeat. You know that your heartbeat is quasi-periodic, so you might want to label each heartbeat, whether it is normal or abnormal. So let's take a look at this example. So we have two patients, patient 1 and 2, and we have their ECG signals. And here we are dealing with two types of heartbeats. One is called N and one is called S. And here, as you can see, for the first patient and for the second patient, their heartbeats are so different that even when the class label, for example, N or S, are the same between the two, these two heartbeats look completely different. And in the meantime, how big is this difference? The interdomain difference actually overshadows the interclass difference. For example, for the first patient, you barely see whether the N and S class have any morphological difference. But you know, for different patients, even if they have the same class label, their heartbeats look very different. So domain adaptation and generalization is designed to tackle with exactly this sort of data. So these are two classes of techniques to mitigate the impact of discrepancies between the distribution of training and testing data from different sources. So we call the distribution of the training data as being drawn from the source domain, although this is technically not accurate, because as we will see, sometimes we may use some data from the other domain, which is called the target domain. which is where you want to really apply this trained model to. So in this case, domain adaptation means that you will use data from one single or multiple source domains and very limited data from the target domain for model training. For example, let's consider the ECG signal thing. So you may have like 10 historical patients. For each patient, you have a 10-minute recording of their ECG heartbeat. Then you may have a new patient coming in, and the new patient only has 10 seconds of recording. So in this case, if you combine these two to form a training set, that is where domain adaptation comes in. And then you have domain generalization. This one is even more challenging. So in this case, you only have multiple source domains for training, but you don't have any training data from the target domain. That is, you only have, say, the 10 historical patients, and you want to train a model that can generalize to any future patient to classify their ECG heartbeats. Okay, so what is the rationale? How does domain adaptation or domain generalization work? So to understand this, we need to understand how exactly deep learning works. So in essence, deep learning is about transforming the raw input data into a latent feature space in which the representation of the input data can be more easily used to complete the downstream task. For example, in our case of ECG heartbeat classification, so the objective of deep learning is to transform these raw ECG signals into a feature space in which it is easier to predict the label of each heartbeat. So here is a generic deep learning neural network. So as you can see from the raw input, we first have a feature learner which maps the maps the raw input into the latent feature space, and then based on the learned features, you have a downstream task solver that is used to complete the downstream task to obtain the final output. Now, the downstream task solver actually directly guides the feature learning. For example, let's take a look at the ECG heartbeat classification example. So that downstream task solver is like, hey, feature learner, just give me some features that can help me classify these ECG heartbeats. And the feature learner is like, okay, you got it, boss. So feature learner does what the downstream task wants, that is to give features that can help classify the heartbeats. So whether we can successfully complete the downstream task largely hinges on whether we can properly guide the feature learner to meet the downstream task's need. So in the case of multi-domain data, what sort of guidance do we want to give to the feature learner? Well, let's say if we just ignore the domain domain discrepancy thing, we do not apply DA or DG, then the guidance we give to the feature learner is to help accomplish the main downstream task on the training data. Remember, most of the training data is from the source domain. For example, for the ECG heartbeat classification thing, the guidance will be just to distinguish between the heartbeats of different classes on historical patients. But this is not good enough because we are going to generalize to new domains like new patients, and a model that performs well on existing source domains does not necessarily perform well on the target domain. That is for example, here, the future patients. So in view of this, for DA and DG, alongside of the main downstream task, we will use a auxiliary task to guide for additional guidance of the feature learner. The auxiliary task is designed specifically to boost the performance on the target domain. That is, the auxiliary task is designed to help the main task to perform better on the target domain. So here we have two questions that ensues. The first one is, now we have two tasks. How can two downstream tasks fit in one deep learning model? And the other is concerning the auxiliary task itself, how do we design it so that it can help boost the performance on the target domain? So the first one, we already have the answer if you have followed the last deep seminar. That is, you use multitask learning. But just as a recap, what does multitask learning do? So multitask learning, more specifically, we are focusing on something called hard parameter sharing this time. So if you want more specific information, you can go back and check our last seminar. But in essence, deep multitask learning, what it does is to use one single feature learner to complete multiple tasks. So here you have a input learner for both tasks A and tasks B, and they share some layers, which is the feature learner, and they use the common features to different downstream tasks and obtain the output for the different tasks. So in the case of DA and DG, this is very simple. We have two task-specific layers. The first one is the main task, no problem. And the second is the auxiliary task, which is either DA or DG. And in this case, for model training, the output of the shared layer, these shared layers, that is the feature learners, is fed to both the main task solver and the DA or DG task solver. But in terms of online predictions, we ignore the DA/DG task completely because it serves only the purpose to help boost the performance on the main task during the training. And after the training, after all the parameters are learned in this network, we do not need it anymore, so we can just drop it. And we only use this stream, the main task stream, to do the online predictions. Okay, so any questions so far? Okay, so it's gonna be a little bit harder to follow from here onwards. So I need you to stay with me, and if you have any questions, please just ask them immediately, because it's gonna get a little bit hard to follow later about the design of the auxiliary task. Okay, so how do we design these auxiliary tasks? So one way to design this task is to guide the feature learner to remove the domain-specific info in the learned features. What this does is that it forces the main task solver not to rely on these domain-specific info to make predictions. For example, in the previous ECG heartbeat classification application, if you do not remove the info concerning which patient this specific heartbeat comes from, then the main task solver may use this information to help classify whether the heartbeat is normal or not, which is not something we want, because we are going to generalize to new unseen patients that will differ drastically to existing patients. So we want no such info at all. So how do we do this? This can be done in many ways. One of the most widely adopted ways is to use something called a domain adversarial neural network, or DNN. I will explain what adversarial means later. And this is especially useful when there is no known labeled target domain data. So this is sometimes called an unsupervised domain adaptation task. So specifically, what you have is here. Sorry, let me just is here. We have this under this multitask learning framework. The DA or DG task solver is what we call a domain classifier, which predicts which domain each input example comes from. So just to recap, the input consists of two parts. One is labeled source domain data, and the unsupervised unlabeled target domain data. This one only appears for domain adaptation. If you're dealing with domain generalization, this will not be available. So you will only have the labeled source domain data, although there will be multiple sources. And in this case, what the domain classifier do is to predict the domain each input example comes from. So, for example, for the ECG heartbeat classification thing, the domain classifier predicts which patient the current heartbeat comes from. And here comes the tricky part. What we want to do is remove the domain-specific info. So how do we verify or make sure that this info is removed? we want to make the domain classifier perform as badly as possible, because if there is no specific info to each domain, then you will expect that the domain classifier cannot tell whether an input feature is from the source domain or the target domain, and also if there are multiple sources, you won't be able to tell which source it comes from. So we want it to perform as badly as possible. And in this case, what we can do is to minimize this this loss function during training. And the loss function looks something like this. It has two terms. The first term is very simple. The main, of course, we want to perform well on the main task, so we just minimize the main task loss. What is special is the second one. The second one, we have this loss function for the domain classifier. So if the domain classifier performs well, then this loss will be small, and will be large if the domain classifier performs badly. So in view of the fact that we want it to perform badly, we want to maximize this loss. And here is where the adversarial thing comes in. We want to minimize the main target loss, but we want to maximize the DA loss. So in this, how do we achieve this? We add a minus to this DA loss. Of course, the lambda is a weighting hyperparameter that tells how important this DA loss is compared to the main loss. But the general idea is that we want to simultaneously minimize the main target loss, but maximize the DA loss. So here is how the adversarial comes in. Of course, in this raw form, this network will not be easily trained. That is, these loss functions cannot be, this whole loss function cannot be minimized very easily. So there will be some implementation tricks as to how to change this into a plus, but I'm not going to go into the technical details here. For now, you just need to know is that all we want to do is to minimize this adversarial loss. So let's take a look at a specific example for the DNN, which is called codets, and the main task here is time series classification. For example, previously the ECG signal is a kind of a time series data. So the ECG heartbeat classification thing can be modeled as a can be modeled as a time series classification task. And this method is called convolutional deep domain adaptation model for time series data, or codets. And so as you can see, we have here this multitask learning framework that is that strictly follows the DNN architecture I just showed you. In this case, the feature extractor or the feature learner is actually a CNN, a convolutional neural network, as it has been shown to work pretty well on time series data. And it is fused with these two tasks. The first one is the main classification task, which uses a single layer of fully connected layer to do the prediction. And then we have the domain classifier, which uses three layers of fully connected neurons to do the domain classification. And for the loss function, let's suppose we have n-labeled source domain training examples, the ith of which has a ground truth label of yi, and the domain origin is di, while its predicted class label by the task classifier is y hat I, and its predicted domain origin by the domain classifier is d hat I. And then we may have some, we have m and labeled target domain examples. They all originate from the target domain, which we call this. I'm sorry, I don't know how to pronounce this in English, but it looks like something like this. And then the jth examples predict domain is this one. So for the codets, the loss function is this one. The first one is the main classification loss on the main classification task, And here L is a multi-class cross entropy loss, which is a commonly used loss for multi-class classification. And the adversarial domain adaptation loss looks something like this. So we have two. This has two terms, but basically do the same thing for the source domain data and the target domain data, which is to predict, which is to quantify how well this domain classifier is doing on each of these training examples. And what we want to do is to maximize this loss to make the domain classifier perform as poorly as possible. So here you have the minus. Okay, so that is it for the for DNN. Apart from DNN, other methods of removing domain-specific info includes, like, you can minimize the divergence, the discrepancy of the data distribution between the different domains. That is, you can change the domain classifier into a function that measures the distance between the examples between the examples. And what you want to do is to make sure that the examples from different sources have minimized the distance between them, so that the domain specific info is removed in the feature space. And also you can generate source-like data from the learned features. That is, even if the learned features come from the target domain, if the generated data from these learned features look like the source, then we may say that the source and target domains, their domain-specific info is missing from the feature space, because if that info is still existent to a large extent, then it is unlikely that the generated data will look like the source data. So in this case, we will remove the domain-specific info to the source and targets. Okay, so that was it for removing the domain-specific info in the learned features. That's one methodology of doing DA or DG. Any questions so far? Okay, good. Then let's do the second part. So the previous methodology was about removing the domain-specific info. Now we have another way of DA or DG, is to explicitly prioritize class affinity over domain affinity. So what does class affinity and domain affinity mean? So most specifically, let's take a look at two different types of examples in the training set. The first one is what I call examples with class affinity. That is, these examples have the same class label, but they are from different domain. They have different domain origins. For example, in the ECG classification thing, you may have both. You may have two heartbeats that are both anonymous, abnormal, or normal, but they are from different patients. The second one is the complete opposite of this, is called examples with domain affinity. That is, they have different class labels but have the same domain origin. For example, you have one abnormal heartbeat and one normal heartbeat, but they are from the same patient. In this case, we want to somehow make these examples with class affinity to be closer to each other than they are to the latter in the feature space. Like, for example, if so in this way, we know that the class affinity is prioritized over the domain affinity. We can achieve this through something called a Siamese network. This is especially useful when there are some known labels from the target domain during the training, but this also works when there is no target domain data, but you have multi-source domain data. So first of all, why is this network called Siamese network? Well, Siamese is a nationality, and if you know about something about the trivia history, you'll know that there was this twin Siamese brothers, who shared one body, and due to the medical conditions at the time they were living, their bodies could not be separated, so they shed their bodies for the rest of their life, and they actually had kids. So which is what was a very legendary story. And the reason why these networks are called Siamese is because they are just like the brothers, the twin brothers. So you have you have this network, and it is actually symmetric. It has two symmetric parts that shares one body, that is the feature learner. So specifically, let's take a look at what each half of this this twin brothers do. The first one is you have label data from one domain. That is a labeled example from one domain that we call an anchor example. And the other one, on the other half, you have you have another example, input example, that is either positive or negative. By positive, you mean that the example has class affinity to the anchor. That is, it has the same class label, but it comes from a different domain. A negative example is one with domain affinity. That is, one from the same domain as the anchor, but has a completely different class label. And these two examples are fed into the same feature learner to obtain their individual representations in the feature space. And we actually compare these two representations in the feature space. So what do we want to do here? We want to make the positive example closer to the anchor than the negative one. That is literally what we are doing here: prioritize class affinity over domain affinity. So how do we do this specifically? Again, we can draw on a loss function. This loss function is called a triplet loss. So note that while this network takes in two examples at a time, actually, when you calculate the loss function, it involves three examples. That's why it's called triplet loss. So specifically, you have a triplet A, P, and N, where A is an anchor example, P is a positive example, and N is a negative example. What we want is that the distance between A and P to be smaller or equal to that of A and N. But note that here we have a hyperparameter that is positive called alpha. What does alpha do? If we don't have alpha, we remove alpha from this, then the network may end up learning the same representation for any input example, because that guarantees that the distance between A and P is smaller or equal to the distance between A and N. In this case, they are equal and equal to 0, and we don't want this to happen. So we have a user set positive hyperparameter as a margin parameter that is used to avoid this kind of situation. Okay, so we have this. From this equation, we will derive the triplet loss. So for a single triplet A, P, and N, the triplet loss looks something like this, which is the max of the two. That is the distance that is diiP minus dan plus alpha. If you look at this is what you do when you move this dan to the left of this equation. And what we want to do is to make it smaller or equal to 0. So we compare it with 0. So in this case, if if this part is larger than 0, then you will see that this condition is violated, and we add a bit of loss to this loss function. But if it is smaller than 0 or equal to 0, then this one is not violated, and then we keep the loss to be 0. So essentially what a triplet loss does is that it penalizes cases where this condition 1 is violated. And so this is essentially doing a triplet loss for one single triplet. And what about the whole training set? That you can extract a whole bunch of triplets from it, and calculate their individual triplet loss and then sum them up. And as for the selection of the triplets, how to build the triplets, there are actually a lot of ways to do this, and I'm not going to go deep into this here. It is actually a pretty vibrant research front, at least a couple of years ago when this Siamese network was first proposed. Okay, so that was it for the Siamese network. Any questions? Okay, good. All right, so previously we mentioned DNN for removing the domain-specific info, and the Siamese networks, which explicitly prioritizes class over domain. But these two both build DANDG into its main network architecture under the multi-task learning framework. But we do not have to do this. This is about model building. Can we not alter the main model, main deep model? But we tamper with the input data. So we can use DANDG for data pre-processing. So an example of this methodology is what we call domain mapping, which maps the source domain data to the target domain using a tool such as a generative and adversarial networks, which I believe Fula covered in previous deep seminars. If you can go check them out. So instead of using the original data, we would just use this mapped data to build the main model. For example, here you have some street scenes, and these street scenes are actually from different domains. For example, let's take a look at the left one because the right one is exactly the same. Left one on the left, this is from one domain. This domain is called GTA 5, and if you are a gamer of some sort, you will know that GTA 5 is a very, very popular computer game. So this is the street scenes from the screenshots of this computer game. And on the right, we have some street scenes that looks like they're from the real world, but instead they are generated using again from the GTA 5 computer game to make it look like real world data. And if you want to say, let's say, do some image classification thing, you have simulated data from the GTA 5 game as training, but you want to use it for classification of real world images, then you can do this transformation first, do this domain mapping first, and then use these pseudo real world scenes generated from GTA 5 as your training example. And in this case, you actually do not need to modify your main network because the input data is already somewhat aligned with the target domain that you want to apply your model to. Okay, so finally, we have discussed multiple ways of doing the DANDG, and they are actually very, very effective in dealing with multi-domain data. But you need to be careful not to abuse it or overuse it when it's not supposed to be used. The first one is something that you should never do. If you have enough labeled target domain data, just don't use DALDG because they will decrease the performance. This is very intuitive. Like if you have 1,000 heartbeats for a new patient, and then which is more than enough to train an accurate model for this person, then why would you need data from historical patients? That would just add to the chaos because it will add heartbeats that do not look like the target patient at all. So this will make your performance decrease. So DANDG is only a substitute plan when you do not have enough labeled target domain data. So just train your model in the target domain if you have enough labeled target domain data. And also, DANDG is definitely not a substitute for a well-designed feature learner that is based on a deep insight into the data, especially based on your domain knowledge. For example, let's go back to the ECG heartbeat classification specifically this figure here. As I mentioned, from a naked eye, can you tell the difference between N and S simply based on their shape? I believe that most of you will say no. So if you can't do this for human, how do you expect a machine to do the accurate classification just by looking at the shape of these heartbeats? In fact, if you go look into medical literature, you will find that the difference between S and N is mostly not reflected from the morphology or the shape of the individual heartbeats, but from the periodicity across multiple heartbeats. For example, for the first patient, you have a clear pattern here, 2S, then followed by an N. So if you can capture this periodicity all across multiple heartbeats, then you might be able to correctly classify each of these heartbeats. And also for the second patient, this one is a little bit more subtle, but if you observe closely, you will find that the S of each S is closer to its preceding N heartbeat than a normal N heartbeat. So they are actually closer to each other when closer to each other in terms of periodicity. So this subtle change in periodicity is the key to classify these two classes. And so in this case, if you simply use a feature learner that looks like the shape, at the shape, especially if your feature learner only takes in one single heartbeat and ignoring everything around it, then diiP and diiP probably won't help you. But if you use a feature learner, for example, if it takes in several consecutive heartbeats at once and only classifies the heartbeat in the middle, that's going to significantly boost your chance of a successful high performance classification. Okay, so in conclusion, what we mentioned today, domain adaptation, domain generalization, these are sets of techniques aimed to address the negative effects to deep learning by the discrepancy among multiple data sources, or in our case, what we call different domains. diiP and diiG can be built into the neural network architecture under the multitask learning framework. The two examples of this methodology are DNN, which is more effective when there is no known labeled target domain data, and Siamese networks, which is more effective when there is actually some known target domain data. So to recap, the rationale behind these two is for DNN, you simply remove the domain-specific info, but for Siamese network, you specifically prioritize class differences over the domain differences. And also, apart from drawing on the multitask learning framework, diiP and diiG can also come in the form of data pre-processing, and also it can come in a variety of different forms that I cannot cover here. So if you would like to explore more, there are some survey papers listed here, so you can check them out by yourself. So the diiP and diiG is actually a very that has drawn a lot of attention from researchers in recent years. And finally, diiP and diiG are not always effective and may even have a negative impact in certain cases, such as the case where you have enough target domain data. So you need to use them wisely. Okay, so this is for the bulk of this seminar. Any questions so far before we move on to the hands-on exercise? Okay, so let's take a look at the hands-on exercise. You can still see my screen, right?
Yes.
Okay, perfect. Okay, so for this hands-on exercise, we will specifically look into domain adaptation with a domain adversarial neural network, that is DNN, I just mentioned. Okay, so specifically, we are going to look at a handwritten digit recognition system problem, which is a very classic problem in machine learning. So let's first import the packages we need. Specifically, there are a couple of prepackaged toolboxes for domain annotation. Here we use a package called PyTorch Adapt, which has built-in various domain annotation algorithms under the popular PyTorch framework. If you want to run this exercise on your own, you need to run this first to install all the necessary packages on your computer. So let's do the importing now. Yeah, so I've already done this, so it's instant for me. So let's load the data. This data is called a MNIST, which is a very, very famous benchmark in machine learning. And the other data set is called MNIST-M. So what's their difference? So here we use the MNIST handwritten digit recognition data set as the source domain. This entails handwritten digits in black and white, like this one. But while for the target domain, we have the MNIST-M dataset, which is basically randomly colored based on the MNIST dataset. So now let's initiate a model. So as you can see, to build this, if you use some pre-packaged tools such as this PyTorch Adapt, it will be very easy for you to actually implement a domain adaptation algorithm at the end. You just need you just need to implement all these all these separate modules, the feature extractor, and also the domain class, the discriminator, which is used for the main task, and you can just fuse them all together to just in a couple of lines to obtain your final DNN model. Specifically here, we are going to use a model architecture proposed in this paper, and which uses this is for image classification. So you have a CNN as the backbone, and we have two MLPs, that is multi-layer perceptrons, as the main task solver to classify the images, and also the domain classifier, which classifies whether it's for MNIST or MNIST-M. So let's first look at how the initial model without any training performs on the target domain, because we are going to do this on the target domain, and actually it's going to take a while. It's going to take a while to run this, but what I can tell you right now is that the initial score will be well below 0.6, which is not good. Okay, it's actually running now. As you can see, 0.5739, not so good. So let's see if we can train the model to make it better. So we're going to train the model. Training the model actually takes a lot of time, so I'm not going to do it right here. You can uncomment this block on yourself if you want to train the model on your own. Here I will just show you how training this model for 4 epochs makes the difference. Specifically, recall that the objective of DNN is to remove domain-specific info from the learned features. So let's see how the source and target domains are separated in the feature space. So this is the initial distribution before we do any training. So as you can see, the source and targets, they are pretty much not well blended with each other. They are pretty well separated, which is not something we want, because this carries too much domain-specific information. And here are the plots after each of the 4 epochs, what the distribution of the source and target domain data looks like. And as you can see, as the training progresses, these 2 domains starts to blend in with each other. So for the 4th epoch is actually pretty well blended in compared to the first the initial state. So in this case, this indicates that we are beginning to remove the domain-specific info in the feature space. So what this does is that it can significantly boost the results on the testing set, that is the target domain. So let's redo the validation and see how it does. Okay, so after just 4 epochs of training, we have already boosted the accuracy score from something well below 0.6 to something like 0.6442. So it looks like we just trained 4 epochs has made a great difference. And in fact, you can train for like 10 epochs, 20 epochs, or 50 epochs, and then the difference will be much greater in this case. So as you can see, DN has truly made a difference for this particular data set. Okay, so that is all for today's deep seminar. Any questions?
Yeah, I have just one question about the representation that you use. It's TSNE or ACP, I don't know, just for the
Sorry,
representation of the distribution. The
could you repeat it?
visualization of the. Yeah, sorry. What do you use for the visualization of the distribution here for the domain?
Visualization. Okay.
Just an SCP or a TSNE? I don't know.
I think it's this one is actually a built-in algorithm by this PyTorch Adapt. So I'm not sure what it is, but I recall you mentioning T. Sorry, on the top of my head, I cannot recall TSNE, the name of. Okay. Yes, maybe. Exactly that. Exactly that. I think that will suffice to create a figure like this. So yeah, okay. That's probably it.
And I have just a second question. Maybe I missed this part. But what is the balance between the source and the target data that you have for this example? Like you have a few example of the target domain.
Okay, so in general, what you it is more likely that you have much more data than you do than the target domain. Much more data from the source than you do than the target domain. But in this specific example, I think that this specific example they have pretty much the same amount of data for that.
Okay.
Let me. But I need to verify that. That's a good question. Let me just let me check this out for you, and including your previous question, and I will make the answers available in the uploaded version of this this seminar.
Okay, thank you very much.
You're welcome. Okay, any other questions? Okay, so I guess that's it, and thank you all. So this seminar will be uploaded. Okay, sorry.
I was just thinking, for your feature extractor, you use a convolutional network.
What you mean is that the choice of the feature extractor.
Is it possible to use transformers to do the feature?
Yes.
Yes.
So basically, multitask learning, whether it's DNN or any other multitask learning networks, you can freely choose whatever feature extractor you want, whatever main task solver you want, although it's mostly multi-layer perceptrons, and also which domain classifier you want. These you can all customize on your own. So if you think transformer is better for your case, then you can use transformer. You can use something like RNNs or some other any type of deep network. Even if it's not a deep network that you can name, as long as it is differentiable in every single step of the calculation, then it can fit here.
Okay.
That's the beauty of deep learning. It's highly modularized. Okay,
yes,
go on.
Secondly, I may have missed this part because I do not have a healthy internet connection. But I
Okay.
use encoders, and I was thinking when you do the feature extraction at the end, is there research about introducing noise to control the overfitting, the risk of overfitting or data?
I mean, introduce some random noise into this architecture to see if it can be more robust, right?
Yes.
I'm not sure if anyone has ever proposed this as a main part of this algorithm, because frankly, it looks like more of a specific data pre-processing trick to do this. You can certainly try to do it, but I'm not aware of any papers that specifically highlights this as one of its contributions.
Okay.
Okay.
Thanks.
You're welcome. Any more questions? Okay, so I guess this is it. So I will include the answers, the more specific answers to the first two questions in the uploaded version, so that you can have a definitive answer.
Just if you have the time, I just have one last question.
Okay,
sorry.
It's okay.
Do you think that model that do pre-training like BERT or something like that do a kind of domain adaptation before fine-tuning? So specification for one task, don't twist task, and it's related to the domain adaptation in a sense.
I'm sorry, the network connection is a little bit poor. Could you type your question in the chat box?
Okay.
Okay. Yeah. It's okay. Just wait a minute. Models like, do you think models like BERT or any other that do a pre-training before downstream is in a sense a domain adaptation method? Okay, that's a very good question. So the difference between pre-training, transfer learning, and domain adaptation, basically how they are connected. In a sense, yes. In a sense, yes. So let's say basic transfer learning. You have a pre-trained model like the BERT model you download from online, and then you add then you add a few layers to it, and fine-tune some parameters for your specific task. That can be viewed as a type of inexplicit domain adaptation, but for domain, this we generally call transfer learning. We do not call this domain adaptation. It's just fine tuning for your specific application. But does it help to transfer your pre-trained model to a new source? Definitely, it will. It will help a little bit. It's just that whether that kind of help will be as significant as explicitly using a domain adaptation model such as DNN, that is unsure. You need to try on yourself. My suggestion is that if you instead you start from the easier methods, that is to just do the model fine tuning to see if it actually works. If it works, then you don't need something more specific, more sophisticated like DNN, but if it doesn't work, then you can start building a DNN that is more, let's say, has more expertise in dealing with multi-domain data.
Okay, thank you very much for your answer.
You're welcome. Okay, any other questions? Okay, I guess that's it. Thank you all, and so see you next time.
Thank you. See you next time.